Hi there. In this video we're going to look at circle theorems. We have 9 circle theorems, and in this video we're going to look at the ones that are inside a circle. So these 5 that are on the left, and we're going to look at what they are and how we apply them. Okay, so on to our first circle theorem. So this first one often isn't given its own status as circle theorem. It's more just as a given fact, but I think it is important enough that I'm going to mention it. So the first one is a triangle formed at the centre is isosceles. So what that means is that if you've got a triangle where one of the corners is the centre of the circle and the other 2 corners are on the circle itself, and then it forms an isosceles triangle. And that's simply because the 2 legs of the triangle are radii, and because they're both the radius of the circle, they're both the same length, which gives us this nice isosceles triangle. So let's look at a couple of examples where we're going to apply this circle theorem. Okay, so here we're given that this angle is 100 and we're asked to find this angle here, which is x. So what we're going to do is, well, because it's isosceles, I know that this angle here must also be x, and I know that all 3 of those angles have to add up to 180 degrees because it's a triangle. So we get 100 plus x plus the other x is equal to 180. So then we can rearrange that and solve for x. So let's simplify first. So 100 plus, well, x plus x is just 2x, is still equal to 180. Now we subtract the 100 from both sides. So we get 2x is equal to 80. Which then gives us a final answer as x is equal to 40 degrees if we divide by that 2. Okay, so in this one we've got x is equal to 40 degrees. Now let's have a look at this next example. This one, quite a similar method. So we're going to use the fact that this is an isosceles triangle to state that this angle here is also x. And then we do a similar trick. We add up our 3 angles and set them equal to 180. So we get 3x plus x is equal to 180. Now in this case, that's 5 x's altogether when we simplify it. So then to get rid of that 5, we divide by 5. So we get x is equal to 36 degrees. Okay, so on to our next theorem. So the angle at the centre is double the angle at the arc. So what does that mean? Well, if we've got an angle coming from 2 points that forms at the centre of the circle, and we've got another angle coming from the same 2 points at the arc of the circle, this circumference, then the angle at the arc is half as big as the angle at the centre, or the angle at the centre is twice as big as the angle at the arc. There's a couple of ways you can think about it. So let's have a look at how we apply this. Now, if at any point during this video you do feel like you want to have a go at these, feel free to pause and have a try, and then once you unpause you can check to see if you got the answer correct. So let's have a look at this first one. So this first one is just a direct application of the theorem. So the angle at the centre has to be double the angle at the arc. The angle at the arc is 40, so know that the angle at the centre is twice as big as that, which is equal to 80 degrees. And this first one, x is equal to 80. Now this second one is drawn in a little bit more of an obtuse manner, so it's presented in a slightly different way. So there's a couple of things we need to be careful of. So this 260 degrees, even though that is an angle and it is at the centre, it's not the correct angle for what we're trying to find, x. If you look here, this x is on the inside. It's the angle that's on the inside of these 2 points, and so now this 2x is between those 2 points. So here, this 260 degrees, it's not in between these 2 points, so we can't use that angle straight away to use this theorem. We are obviously going to need to use that angle, just in a slightly different way. So what we need to find first is we need to find this angle here. Now that angle there is not too tricky to find because we've got 2 angles that are around a point. I know that angles around a point add up to 360. So, to work out what that green angle is, I'll just do 360. I'm going to take away the 260, and that leaves me with a final angle of 100 degrees there. So that angle there I know is 100 degrees. And now we can apply our circle theorem because this is the correct angle. Again, it looks slightly different because this point has been dragged over here, but that still is an angle that's on the circumference of the circle. It's on the arc, so it's still half as big as the one at the centre. So to work out the final answer, we need to do x is equal to 100. This time we're dividing by 2 because the one at the edge is half as big. So we get x is equal to 50 degrees in this case. There we go. So on to our last one now. So our last one is combining this circle theorem, but it's also using angles in parallel lines. If you're told that two lines are parallel, it's a pretty good bet that you're going to need to use that fact at some point. So let's have a look at how we can do this. Okay, so let's apply the circle theorem first. So similar to this one, the two angles that are related are this angle, and the one at the centre is twice as big as the one at the edge. So how can we write an expression for this one at the centre of the circle? Exactly, if this is x, then this angle here has to be 2x, just an application of this theorem. Okay, so now we need to use the fact that we have parallel lines. So if we think back to our parallel lines video, we've got our transversal that crosses these two parallel lines here, which means that this acute angle and this acute angle have the same value. Now, can you remember what type of angles they were? We've got two choices for parallel lines, corresponding or alternate, and remember what those two are. Exactly, they're alternate angles. So we say alternate angles are equal so I can tell that this angle here is also 2x. And now we're really close because we've got a lovely triangle here, and we know all three of the angles, or we know expressions for all three of the angles. So let's add those up. So we get x plus 2x plus my 102 have to equal 180. Again, because angles in a triangle add to 180. So now I can rearrange this. So I'll do two steps in one here. I'll simplify the x and the 2x to make 3x, but I'll also subtract this 102 from both sides. So 180 take away 102 is 78. So now all I need to do is divide by that 3. Okay, so 60 divided by 3 is 20, 18 divided by 3 is 6, so we get x is equal to 26 degrees. Okay, so on to our third circle theorem. Angles formed on the same arc are equal. So what does that mean? Well, that means if I start at one point and then bounce off the edge of a circle and end at a different point, it doesn't matter where I bounce off, those two angles are going to be the same. So just to illustrate this, if I start here and end here, if I trace out this blue angle, well, that's up to there and down, so I've started and ended at the same point. And similarly, if I trace out this blue angle, well, I can start and end at the same point as well. So because I've started and ended at the same point, and I've gone to the edge of the circle in each angle, those two blue angles are the same. And it's the same argument for why these two green angles are the same. I just start and end at different points for the green ones than I do for the blue ones. Okay, so again, let's have a look at how we apply these. So I've got this example here. So this is a direct application of the circle theorem, but again, we need to be a little bit careful in exactly which angles are equal to each other. So let's have a look and see if we can work out what this blue angle y is first of all. So to trace y out, I can start there and end there. If you look, I start here, I come up, and then trace out the angle y at the edge here. And now which other angle, starting here and ending here, can I trace out going to the edge of the circle? Exactly right. If I start here and end here, I can trace out this 40-degree angle. So because I can trace the 40-degree angle and the y out, starting and ending at the same point, I can say that y is equal to 40 degrees. Okay, let's have a go at this x now. So to trace x out, I can start here and end here. So if you look, if I trace down here and then up to this point here, then I've traced out x. Now, which other angle can I trace out that starts here and ends here? Exactly, this 30-degree angle, down here and up. So I know that x is equal to 30 degrees. Okay, so let's have a quick look at this one now. So we've got to take a couple of extra steps here, but that's absolutely fine, we can manage. So we've got x up here. Now it would be really nice, because x is in this triangle, it would be really nice if I knew these two angles here, which we can work out. So let's have a look at this one first. So this triangle, or this angle here, if I start here and end here, well then I can trace it out like that. So then we need to look, are there any other angles that go to the edge of the circle that I can trace out starting from this point and ending at this point? And it turns out there is, and it's this 60-degree angle. So if I go down here and back to there, and I've traced out that 60-degree angle. Now I've got to be really careful because this 80-degree angle doesn't count. Even though I can trace it out, it doesn't go all the way to the edge of the circle. So this one's not 80 degrees, but that one is 60 degrees. Okay, so now we've got this triangle here, and again it would be really nice if I knew that angle there. Now that angle I can work out because if we look, it's on a straight line around a point with this 80-degree angle here. So to work out this green angle, I do 180, I take away the 80, and that gives me 100 degrees. So this angle here is 100 degrees. And then in my green triangle, I've got, they add to 180, so I can now work out what x is. So if I do my 180, oh dear, 180, if I take away that 100, and then take away that 60, the angle that I'm left with is 20 degrees, and that is our value of x. Perfect. Okay, so last one now for this circle theorem. So this one looks a little bit more complicated, but it isn't all that, it's not much more complicated. Okay, and in fact there's fewer steps than there was in this one. Okay, so let's have a look. So this x, we've got a couple of ways we could go about this. I know that this x is the same as this x, or this angle here. So it could be, maybe there's an easier way to work that out. But looking at the diagram, I'm not necessarily sure it's easier to work out this angle straight away. So let's look at what we can work out from these other angles. So this 45-degree angle here, if I trace that out starting from this point and this point, I can trace out that angle there, so that's 45 degrees, but I also know that this angle is 45 degrees from the circle theorem. If I start here and trace it out, and that gives me that that is 45 degrees. And now we're on a roll. We can see where we're going to go here, because if you look, we have a triangle that we know all the expressions for all the angles for. And so we've got this angle here, which is 30 degrees. we've got this angle here, which is x plus 80 degrees. And we've got this angle down here, which I know is 45 degrees. And all the while we know that angles in a triangle have to add up to 180. So we're really close now, we can work this out. So let's simplify first of all. So 30 plus 80 is 110, plus 45 is 155, plus my x is equal to 180, and then we can subtract the 155, and that gives me that x is equal to 25 degrees. Okay, so on to our fourth circle theorem. A triangle in a semicircle is right-angled. So if we have a diameter of the circle that goes through the middle and that chops the circle into two semicircles, and we form a triangle at the edge using that diameter, and I know that it's a right-angled triangle. Again, this one is really just an application of this second circle theorem. The angle at the edge is half the angle at the centre, but students often forget this one when they're faced with a question, so I do want to do a whole little part of this one. So triangle in a semicircle is right-angled. So we've got a couple of examples here, and now when we look at combining these theorems, this one will feature a bit more prominently, but for now we'll just do the two examples. So in this one, we know one of the angles in this triangle, and we're asked to find this second angle. You might think, well, we can't find this angle if we don't know two of the angles in a triangle, but we do know two of the angles in a triangle. This is in a semicircle, so I know that this angle must be right-angled, which means that x, well, 30 plus this 90 degrees plus our x degrees, well, they're the three angles of our triangle, so they have to add up to 180. So let's rearrange. 30 plus 90 is 120, and then 180 take away that 120 is equal to 60 degrees. So x is 60. We can do a similar trick here. Again, we know that this angle has to be a right angle because it's a triangle in a semicircle. So then I know that x plus this 3x plus this 90 degrees has to be equal to, again, angles in a triangle add up to 180. So let's subtract the 90 and simplify. So we get 4x is equal to 90 degrees. And so then divide by the 4, I get x is equal to, well, half of 90 is 45, half of 45 is 22.5 degrees. Okay, so on to our fifth and final circle theorem of part 1. Opposite angles in a cyclic quadrilateral add up to 180 degrees. So there's a lot of words in there that need deconstructing. Say cyclic quadrilateral first of all. Well, quadrilateral is just a four-sided shape, and it's cyclic if all four of its corners are on a circle. So if we have a cyclic quadrilateral and the opposite angles, so I've drawn a pair of opposite angles here, the other two angles are also opposite, but opposite angles in the cyclic quadrilateral always add up to 180 degrees. So let's have a quick look here. So the first thing we need to think about, well, once we've spotted we've got a cyclic quadrilateral, is to identify pairs of opposite angles. And so let's have a look. So y here, which angle is that opposite to? Is it the 100, the 60, or the x? Exactly. That y is opposite the 100 degrees. So I know that 100 plus that y has to be 180 degrees. So I know that y, if I subtract the 100, is 80 degrees. And now let's look at x. Now x is opposite that 60. So I know that x plus 60 have to add up to 180 as well. So 60 plus my x is 180. So I know that x is equal to 120 degrees. There we go. Onto this one. Now this one's a little bit trickier. You might notice that we don't have a quadrilateral here, we have a pentagon. It is still a cyclic pentagon, but it's not a quadrilateral. And the thing we need to spot, however, is that, well, actually we do have a cyclic quadrilateral. In fact, we've got two cyclic quadrilaterals. Let's draw them on now. So we have one cyclic quadrilateral here. And we have another cyclic quadrilateral here. Okay. So what we need to do is we need to apply this circle theorem twice. And we can then use the angles we calculate to work out what this value of x is. So let's have a look at this green cyclic quadrilateral first. Well, which angle is this 120 degrees opposite? Exactly. It's opposite this angle that is inside the quadrilateral. It's not the whole angle, it's just the angle that's inside this green quadrilateral. And so that is opposite to 120, and so it needs to add up to 180. So I do 180, take away the 120, and that gives me 60 degrees. So now this angle here is 60 degrees. And we do a similar thing with this red quadrilateral. So opposite to the 100 is this angle here. And I know that, again, 180 minus the 100 is equal to 80 degrees. So now that this red angle here is 80 degrees. And what shape has that given us now that we know the angles of? Exactly, we've now got a triangle. And this might get a bit messy, I'll draw it on in blue. We've got a triangle that we now know all the angles for, or we know two of the angles and we can work out the third one. So I know that 60 and 80 and x have to add up to 180. 60 plus 80 plus my x have to add up to 180 because they're in a triangle. So let's simplify. 60 plus 80 is 140. Subtract 140 from both sides. And we get x is equal to 40 degrees. So the trick to that one was spotting, well, first of all, that we could break this pentagon up into several different shapes, including some quadrilaterals and some triangles. Okay. So we've done all the circle theorems that involve shapes that are wholly inside our circles. And in the next video, part 2, we'll look at these remaining 4, which involve things like tangents.